Imagine jumping from an aircraft at 15,000 feet. The wind screams past your ears at more than 120 miles per hour. Below you, the ground looks impossibly far away. Then, in less than 3 seconds, a bundle of fabric no larger than a backpack transforms into a life-saving machine capable of stopping a human being from falling to their death. Most people never think about this, but every parachute carries a responsibility measured in lives. Imagine jumping from an aircraft at 15,000 feet. The wind screams past your ears at more than 120 miles per hour. Below you, the ground looks impossibly far away. Then, in less than 3 seconds, a bundle of fabric no larger than a backpack transforms into a life-saving machine capable of stopping a human being from falling to their death. Most people never think about this, but every parachute carries a responsibility measured in lives. Imagine jumping from an aircraft at 15,000 feet. The wind screams past your ears at more than 120 miles per hour. Below you, the ground looks impossibly far away. Then, in less than 3 seconds, a bundle of fabric no larger than a backpack transforms into a life-saving machine capable of stopping a human being from falling to their death. Most people never think about this, but every parachute carries a responsibility measured in lives. Every parachute starts with petroleum. The story often begins in oil-producing regions such as Saudi Arabia, the United States, Canada, and the United Arab Emirates. Crude oil travels hundreds or even thousands of miles to massive petrochemical facilities, where engineers separate and refine hydrocarbons into the building blocks of nylon. Think about this. A material trusted with human lives begins as ancient organic matter buried underground for millions of years. Inside chemical plants, manufacturers produce nylon 6, one of the strongest synthetic fibers ever developed. The process combines adipic acid and hexamethylnediamine through polymerization. Long molecular chains form microscopic structures that give parachute fabric its incredible strength-to-weight ratio. Most people never think about this, but a single kilogram of finished nylon contains billions upon billions of interconnected molecular bonds. The finished polymer emerges as tiny pellets no larger than grains of rice. These pellets travel by rail, cargo ship, and truck to textile factories across the world. A shipment may cover 5,000 to 10,000 miles before reaching its destination. By the time those pellets arrive, they've already crossed oceans, mountains, deserts, and international borders. Then comes one of the hidden stars of parachute manufacturing. Ultra-high-strength fibers used in suspension lines often come from advanced materials such as aramid and ultra-high molecular weight polyethylene. These fibers can be stronger than steel by weight. A line only a few millimeters thick can hold hundreds or even thousands of pounds under load. And this is where the numbers become almost unbelievable. Then comes one of the hidden stars of parachute manufacturing. Ultra-high-strength fibers used in suspension lines often come from advanced materials such as aramid and ultra-high molecular weight polyethylene. These fibers can be stronger than steel by weight. A line only a few millimeters thick can hold hundreds or even thousands of pounds under load. And this is where the numbers become almost unbelievable. A typical sport parachute canopy may contain more than 600 square feet of precisely engineered fabric, yet the entire system often weighs less than many household vacuum cleaners. Manufacturers spend years balancing strength, flexibility, weight, porosity, and durability. If the fabric weighs too much, performance suffers. If it weighs too little, safety margins disappear. Environmental challenges follow every stage of production. Petrochemical refining consumes large amounts of energy. Fiber manufacturing requires heat, water, and transportation networks spanning continents. Some manufacturers now recycle industrial nylon waste and adopt lower-emission production methods. But here's the question few people ask. Once the raw materials arrive, how do engineers transform fragile-looking threads into equipment trusted by soldiers, astronauts, and skydivers around the world? The transformation begins with fiber extrusion. Nylon pellets enter heated extruders operating around 260 degrees Celsius or 500 degrees Fahrenheit. Inside, rotating screws force molten polymer through tiny spinnerets that resemble showerheads designed at microscopic scale. Streams of glowing material emerge and cool into continuous filaments moving at speeds exceeding 50 meters per second. Next, giant drawing machines stretch the fibers under carefully controlled tension. Workers monitor temperatures, speeds, and alignment, while sensors measure consistency thousands of times per second. As the fibers stretch, molecular chains align and strengthen. What happens next surprised even experienced engineers. A strand thinner than a human hair becomes strong enough to help save a life. Those fibers move directly into weaving halls filled with the rhythmic thunder of industrial looms. Some looms operate at hundreds of insertions per minute, interlocking warp and weft threads with extraordinary precision. The air carries a faint warm scent from machinery and lubricants. Everywhere you look, fabric grows continuously from machines that never seem to stop. Fresh off the looms, the fabric enters one of the most critical stages in the entire process. Engineers apply specialized coatings that reduce air permeability and improve durability. Large finishing lines move fabric through controlled heating zones operating between 150 and 210 degrees Celsius, or 302 to 410 degrees Fahrenheit. The material glides through rollers with soft mechanical hum, while powerful ventilation systems pull away heat and vapor. Now the fabric reaches a stage where precision becomes almost unbelievable. Computer-controlled cutting systems spread giant layers of parachute cloth across vacuum tables. Laser-guided cutters slice complex aerodynamic panels with tolerances often tighter than 1 millimeter. Every curve, every angle, and every seam allowance must match the engineering blueprint exactly. A single inaccurate cut can affect how the canopy flies through the air. Workers carefully organize hundreds of individual fabric pieces into complete canopy sets. Imagine assembling a giant three-dimensional puzzle where every component must align perfectly. Color markings guide technicians through the process, but experience matters just as much as technology. Even after decades of automation, human eyes still catch details that machines occasionally miss. The sewing department feels almost like an aerospace laboratory. Industrial sewing machines run at speeds of 3,000 to 5,000 stitches per minute, while operators guide delicate fabric through complex seam patterns. The rapid clicking sound fills the room. Row after row of reinforced stitching locks panels together, creating structures strong enough to withstand forces generated during high-speed deployment. Next come the suspension lines. These incredibly strong cords connect the parachute canopy to the harness system. Technicians measure each line with extraordinary accuracy because even small differences can affect stability during descent. Hundreds of attachment points receive reinforcement stitching. The work demands patience, concentration, and years of training. Then comes harness assembly. Heavy-duty webbing passes through industrial sewing stations where machines create dense load-bearing stitch patterns. Some harness sections must withstand forces exceeding several thousand pounds during deployment. Workers inspect every connection repeatedly. There is no room for shortcuts when human lives depend on the outcome. Finally, the completed parachute enters packing and preliminary deployment testing. Technicians fold hundreds of square feet of fabric into remarkably compact containers. Every fold follows a specific sequence designed to ensure proper opening. Most people never think about this, but a parachute is not simply packed. It is engineered to unfold in precise choreography, measured in fractions of a second. And just when the parachute appears finished, the most demanding stage of all begins. Engineers are about to test whether months of manufacturing can survive the violent forces of real-world deployment. What happens inside the testing facility determines whether this parachute earns the right to leave the factory. The moment a completed parachute leaves the assembly floor, it enters a world ruled by sensors, scanners, algorithms, and relentless inspection. Most people imagine quality control as a quick visual check. The reality looks more like an aerospace laboratory. Every component must prove it deserves to be trusted with a human life. First, high-resolution AI vision systems inspect every visible section of fabric. Cameras capture thousands of images while machine learning software searches for defects such as missed stitches, fabric contamination, weave irregularities, discoloration, and microscopic tears. Some systems can identify flaws smaller than half a millimeter. What the human eye might miss in a fraction of a second, the AI never overlooks. Next, laser measurement systems verify dimensions across the entire canopy. Bright scanning beams sweep across fabric surfaces, while software compares every measurement against engineering specifications. Tolerance limits often remain within 1 millimeter. If a panel sits outside acceptable limits, inspectors immediately flag the parachute for correction or rejection. Then comes strength testing. Specialized machines grip suspension lines and slowly apply increasing loads. The equipment measures elongation, braking force, and material behavior under stress. Hydraulic systems generate forces reaching thousands of pounds, while sensors record every microscopic change. The sound of tension building inside the test chamber creates a silence nobody wants to interrupt. Manufacturers also conduct fabric permeability tests. Air flows through carefully measured samples while instruments calculate resistance and porosity. Even tiny changes in airflow can affect deployment performance. Think about this. Something as invisible as air passing through fabric can determine how safely a parachute opens thousands of feet above the ground. Some facilities perform accelerated aging tests designed to simulate years of use. Powerful ultraviolet lamps mimic sunlight exposure. Environmental chambers cycle temperatures from freezing conditions to extreme heat. Humidity systems recreate tropical climates. In just a few weeks, engineers can study were equivalent to years of real-world operation. And this is where it gets truly extraordinary. Some military and aerospace parachutes undergo live deployment testing using weighted dummies, cargo systems, or aircraft drops. Cameras recording thousands of frames per second capture every stage of deployment. Engineers analyze inflation symmetry, opening speed, line tension, and descent stability. What appears smooth to the naked eye reveals an incredible world of physics when slowed down. Despite all this technology, there is one moment where human skill still beats machines. Experienced inspectors perform final hands-on examinations by touch. Their fingers move across seams, webbing, stitching, and connection points, searching for subtle irregularities. Years of experience allow them to detect issues that even advanced systems occasionally overlook. In many facilities, rejection rates range from 1 to 5% depending on product type and inspection stage. That may sound small, but it means thousands of components never leave the factory. Manufacturers would rather discard expensive materials than risk a single failure in the field. Safety always wins over production speed. Before shipment, manufacturers document every inspection result, material batch, test record, and certification. Standards may include military specifications, aviation regulations, and internationally recognized quality systems. By the time a parachute reaches a customer, it carries an invisible history of measurements, tests, and approvals stretching back through every stage of production. But here's the mystery that remains. How many parachutes does the world actually produce each year? How has this industry transformed over the last half-century? And some of the numbers you're about to hear sound almost impossible to believe. The United States remains one of the largest producers and users of advanced parachute systems, driven by military, aerospace, and recreational demand. China has rapidly expanded textile and manufacturing capacity. France, Germany, and the United Kingdom maintain strong positions through specialized aerospace and defense industries. Together, these countries account for a significant share of global production and innovation. Most people never think about this, but tens of thousands of workers contribute directly to parachute production worldwide. Chemists develop polymers. Textile engineers design fabrics. Machine operators run weaving systems. Skilled technicians perform stitching and assembly. Quality inspectors verify every critical detail. A parachute may appear simple, yet it represents a combined effort of entire industries. Over the last 50 years, parachutes have changed beyond recognition. Older canopies often relied on simpler round designs. Modern ram air parachutes function more like flexible wings, allowing remarkable control and maneuverability. Advanced synthetic fibers dramatically increase strength while reducing weight. Computers now assist in design, testing, and manufacturing processes that once depended entirely on manual calculations. Did you know that some spacecraft returned to Earth rely on parachutes larger than many houses? These giant systems deploy in carefully timed stages to slow capsules traveling at tremendous speeds. Without them, astronauts, scientific equipment, and valuable mission data could be lost in seconds. The same basic principle that protects a skydiver also helps bring space exploration safely home. Did you know that some cargo parachutes can safely lower vehicles, supplies, and equipment weighing several tons? Military logistics teams use these systems to deliver critical resources into locations where conventional transportation cannot reach. Watching one of these massive canopies inflate feels less like fabric opening and more like a building suddenly appearing in the sky. And here's perhaps the most surprising fact of all. A parachute that may save a life during a deployment lasting only a few minutes often requires months of manufacturing, testing, documentation, and certification before it ever reaches a customer. The time spent building confidence into the product far exceeds the time it spends performing its most important job. Think about the journey you've just witnessed. What started as crude oil deep beneath the ground became microscopic polymer chains, then fibers, fabric, suspension lines, and finally a precision-engineered system trusted in some of the most demanding situations imaginable. Along the way, countless workers, engineers, technicians, and inspectors contributed their expertise to a product most people rarely notice. The next time you see a parachute opening high above the ground, you'll know you're looking at far more than fabric and cords. You're looking at chemistry, physics, advanced manufacturing, quality control, and decades of engineering knowledge working together in perfect synchronization. Most people see a parachute. Now you can see the extraordinary world hidden inside it. The next time you hold one of these in your hands, remember, it didn't just appear. It was born from the earth, shaped by fire, perfected by technology, and approved by the strictest standards in the world. That's not just a product. That's a masterpiece of human engineering. If you want to go deeper into the hidden world of manufacturing, tell us in the comments what product you'd like to explore next. Like this video, subscribe to the channel, and we'll see you inside the next factory.